and can hardly stand, but I was so much looking forward to giving this talk because it actually contains an idea that totally fascinates me, and it's very recent, and it links a lot of the stuff I've done with different people in the last year, and I think it might actually influence, or it might help you, or give you a perspective that helps you to design quantum machine learning algorithms, if you want to do so. Let me make this bold statement. The background of this is that I tried to do quantum neural networks for basically 4 years, so always, everything I worked on, I always thought, no, it would be so cool to like have a quantum version of a neural network model. I tried to kick quantum theory into the shape of neural networks, and then I gave up on that. And I went to kernel theory, which is absolutely unsexy in machine learning circles because it was like very like famous in the 90s, but now no one's talking about it anymore much, at least in research. And what I found was just paradise. Like all these things I tried to force for these years now actually work. And I want to show you, I hope I can convince you a little bit like that this is true. Sorry, this is not my affiliation, Microsoft, obviously, but so one of the papers I want to give a teaser on was written while I was the intern there. So maybe I should have taken that out. I want to claim some coolness. Okay, Peter's advertising this book, which is really nice. I just want to tell you, so it's almost, we're just doing the last proofreads. It will come out with Springer. This is Photoshopped, so this actually doesn't exist yet. But so what's the idea of it is a bit like to shortcut if there are people who want to get into the field, like basically just to take the barriers a little bit away from it. And summarize concepts and methods you find like in several papers. So it's not a literature review or something of like all the papers you know. But for example, if you always wanted to know how to take a sign out of a swap test or how to encode information into quantum states and what are the efficient algorithms and what conditions they take or something, it might be also interested for you. I hope that, yeah, it helps us all a little bit. Second advertisement, if you want to meet your friends again in November, this is the Quantum Techniques for Machine Learning second edition. The first one was in Verona, and this one is in KwaZulu-Natal. And the last announcement is that if you want to see those beaches every day, there's also a postdoc position in Francesco's group. So, okay, and lastly, so I will mainly talk about like a paper with Xanadu where I'm working, but also like mention a paper from last year and something, as I said, like that's coming up. Okay, a lot to do. So if you just want to have the executive summary, this is basically your slide. This is the idea. So I think that in kernel methods and in quantum computing, we're doing almost the same thing. Basically, in quantum computing, we want to like implicitly compute in Hilbert space, and that Hilbert space can be infinite dimensional or exponentially large. I mean, it's vastly larger. But we actually like just manipulate like an efficient number of qubits. And kernel methods have a very similar idea. So the idea is that I implicitly compute in a vastly dimensional feature space, often also infinite dimensional. But what I do, I just like stay with my computations on the original input set. So I basically like just compute distances between data points. But we can show that what happens in a sense, or at least theoretically, is that you compute in a very, very large feature space. So now you will immediately guess what I'm trying to do. I want to encode like information into quantum states that maps the information theoretically into a Hilbert space, and I want to associate this Hilbert space with a feature space and see what we can do in terms of data analysis. What will come out of it is 2 ways to write quantum machine learning algorithms. Both ways are for intermediate term devices, so it might be interesting. And for me personally, if I have enough time, I will afterwards say like why I think it actually solves the problem of doing quantum neural networks. Well, that's a teaser actually. Yeah. Okay, so I will try to connect those. The 2 concepts, so I only have pictures and I'm not doing, so kernel methods are, the theory is really deep, which is strange for machine learning, and it's vast, and it's beautiful actually, to be honest. And I will completely cut that out, I'll just do pictures here. Basically, we need the concept of a feature map and a feature space. The idea is I've got data. I'm always thinking about supervised learning. I'm sure a lot can be done for unsupervised learning, but correct me if I'm kind of like very limited in that idea. Okay, so I've got data in my original space. The idea is I want to classify, I want to find decision boundaries, and a feature map maps that data into, so the word you can also use for in a lot of other senses. How I use it here is to map into a higher dimensional space. And you can hope that this feature map makes your data easier to analyze. For example, it makes it linearly separable. And you can think of it as a neural network, maybe it selects features out, so it compresses, and this stuff like blows it up. But the complexity is hidden in how to blow it up, right? So it's not an easier problem, I guess. And just to give you 2 examples of how this immediately, you can see how this works. Let's say your data is 2-dimensional, and you've got like XOR function data, I would call it. So you can't, and you only have a linear model, so you can't actually classify this data because you only have 1 linear decision boundary. You can't really cut it. Now we go to 3 dimensions. In the 3rd dimension, we artificially compute. We just say it's x1 times x2. And like, so if this point is 1, 1, and this is minus 1, minus 1, they will both map in the 3rd dimension to the positive subspace and the other ones to the negative. So you can cut through. And the other one is like a circles data set gets very easy to separate. If you introduce this feature, then you can cut through, and it lays it on a parabola, basically. So these are like typical examples you find. Okay, this is already like half of the theory. The second thing we need is a kernel, and also a kernel is actually defined a bit more complicated. So it's basically a function that has 2 slots, and it's defined on an input space, and it's positive definite. But for everything that we would need here, it's just like a kernel is just a measure for the distance between 2 data points. And I'm just trying to like draw this a bit, what that means. So let's say I put in the first slot, I put this like blue data point, and this shaded area is now the value of the kernel. And basically, I like show you the value of the kernel for like any x that I can put in here. And this is like the idea of like, for example, a Gaussian kernel. And it's obviously a distance measure because like if I have a data point here, it gets a very small value of the kernel, and something closer gets a higher value of the kernel. But it's not something as boring as just Euclidean distance. How can you build a classifier out of that just so that you get a feeling for, I mean, there's a very stupid way. You basically just like compute what is the similarity of a new input here, this yellow thing, with the blue data. And you just say, okay, this is the kernel, so the distance between those 2 according to my function, and the distance between those 2, so basically how much shaded area does it have? And then you look at the same thing for the red data, and then you just check which one is larger. And this is a lot of kernel methods you can understand in that way. Let's put it like that. I mean, they're obviously a bit smarter. And then in kernel methods, the big thing is basically to like put weights on kernels, so say, or on data points, so learn weights, how much do I weigh this data point and like this distance. But the second thing is that I actually can vary, like, for example, the variance of the kernel, or like my distance measure. I can like learn which one is a good one. And this is just, so this is, I don't know if anyone has looked at this, but this classifier I was just formulating is exactly what we do in this paper from last year. Actually, it must have been December, no, it wasn't this year. Anyways, the idea of this paper was basically just to say, like, guys, let's turn it around. Let's stop to translate machine learning models into quantum models and like try to kick quantum theory. But let's look at what a circuit and an absurdly short circuit can actually do. And you see, this is my circuit. It's just like 3 gates, and it's constant like runtime. It's just always 3 gates. The only thing I have to do, I have to like have a data preparation circuit. And so basically, this little circuit does. I thought it was quite a neat thing. You can show that it does exactly this kernel method we were talking about, this kernel classifier with this type of kernel. 1 minus like the distance. So if the distance there is like the squared distance is very small, then my kernel is very strong. And just to I wonder why the background is always not showing. Anyways, and just to show you with some data, like we took just 2 classes of the iris data and like standardized it to lie nicely, and then you have to normalize it for this algorithm, which can introduce some subtleties, but it's usually not so bad. And then, like, if you now say the darker points are the ones weighed stronger by the kernel, this is basically the picture you get, and you see this input, the black dot would now get a blue flag. You see that immediately, right? Okay, so this was like kind of relating back to this work. But actually the real like idea of kernel methods, well, I only realized what power they have later. Okay, so we're almost there. Now there's these kernels and feature spaces are 2 coins of the same thing. So they are really closely related. And how are they related? A kernel on the original space, you can show if it's like a positive definite function. There is a feature space for every such kernel, so that feature map vectors or vectors in this feature space correspond to this kernel. Does that make sense? So I kind of like took 2 vectors in the feature space, I take the inner product, and I've got a kernel function. And now you should immediately know how to make a quantum machine learning algorithm out of that, and that's actually the first idea I'll introduce, which is, well, okay, I'll leave it to you. But so basically this, yeah, okay, let me just continue. Okay, so let me say this. So this is obviously an inner product, and you see already this looks very much like a quantum state. So if you can just like have an inner product of quantum states and like kind of associate with a kernel, you actually have already a lot of methods that you can think up. Okay, so how do we relate this thing to quantum physics? And this idea is to just, is something we actually do all the time when we do quantum machine learning algorithms. It's the process of encoding information and inputs into a quantum state. And this is my feature map. It exactly like fulfills the definition of a feature map. So my feature map is like I take an input and just like create some quantum state that somehow depends on that input, and I don't care how. And now this like input encoding gives rise to a kernel. So whatever input encoding you use, and most of you use them when you create these algorithms, gives rise to a kernel. I'll show you a couple of examples. Something I usually call basis encoding is like if you have a, you have data that's given as a bit string, and you associate a quantum basis state, computational basis state with this bit string. And now, like obviously an inner product of two such states is nothing else than the Kronecker delta. So information encoding gives rise to a kernel. Second thing I usually call amplitude encoding. By the way, I think a lot of discussions about work would be very much easier if people would reveal their information encoding strategy right at the beginning, because that changes everything, and then it makes it a lot easier to talk about these things. Anyways, so you've got a normalized vector, and you encode things into amplitudes, and the inner product of two of these vectors will just be the inner product of the input states. So this is called a linear kernel in machine learning. Patrick had actually the papers I give here is just like, so this was, it's just examples like from a very early one and a very recent one that uses this, but there are a lot of papers like use that. Then Patrick had this really nice insight that if I take, what happens here is I do the same encoding, but I take two copies of it. So instead of having like it encoded in one qubit, I prepare that state in one qubit and then again in a second qubit. And what happens with the kernel, I've got a polynomial kernel. And if I've got D copies of the state, I have a D here. So this is a polynomial kernel in machine learning with like zero offset. But I think you can also quite easily get the offset in there. This is a beautiful paper, I think, from tensor networks and machine learning, where someone like Miles Staudenmeier uses this idea to like encode these things into, so every feature is now encoded in a qubit. So like x1 is encoded in the first qubit, x2 is encoded in the second qubit, and this gives actually rise to a cosine kernel. So now you see how this like framework gives you immediately like a new interpretation of a lot of work, like because machine learning that he does might be interesting to analyze like in terms of this framework. And what I analyze, because at Xanadu we do CV systems, and luckily I don't have to actually ever explain to you what that is, because we basically just need the idea. But just to show to you, we actually we encode information to squeeze state. So this is like one mode squeeze state. There's like a parameter, like you call it the amplitude or the absolute value, and a phase parameter, and it looks horrible. And you see, for those people who don't know about CV systems or Fock bases, instead of having here a superposition of 0 and 1, we have a superposition of an infinite number of basis states. And it looks rather nasty, right? But again, we can just do the same thing. We just like encode like our x1 into the phase here, into that second thing. And the first slot we just like put as a constant. We tried it the other way around also for some time, it's also possible, but this one is a bit nicer, we found. And then that kernel looks like that, and you see your input appears here as a phase vector. Something really nice is when you vary the C, so this constant that you choose is a hyperparameter, you actually, so this is the kernel function plotted, you actually vary the variance of the kernel function, which is quite nice because that's what people do with Gaussian kernels. They learn how wide it has to be. Okay, and now lastly, I just want to show you those two approaches. And this is a total mistreatment of the representative theorem, but it matches so nicely when you like formulate it a bit like in pub language, how these two approaches actually connect to two sides of doing machine learning. So the representative theorem is something to take serious, and it's mathematically demanding like theorem, but if you boil it down absurdly, you would say a trained linear model. So if I try to find like a linear decision boundary in feature space, and now, so I write a linear model, then I train it, so I find that perfect decision boundary under a certain cost function, which is very general. So for example, squared loss, like what we usually use, is totally like in the sphere of this theorem. So like I have got like this linear model. It can always be rewritten as a kernel function. So where here, these are inner products of the feature space. And by actually changing kernels, I can actually build different models. So now machine learning people, what they do in kernel methods, so this is kind of what opened up the theory to it, because they say we don't have to like go into an infinite dimensional space and learn a model, which would mean to learn infinite dimensional amounts of parameters. But we can just like stay in input space, and if this is efficient to compute, we can just like use our input vectors. So we implicitly compute in this huge space, but we never ever touch it. And this is like what's usually like sold, or what's the heart of kernel theory, and how people made sense of why these methods work. You know, a support vector machine is like a kernel method, so you also find these kernels like somewhere in there. Okay, and so the first thing I will do, and also executive summary, and it won't hurt, it won't take long, is just to use a quantum computer now to compute kernels. So the quantum computer is basically a little device that I have in my drawer or something, and the only thing it does, it produces kernel functions. It evaluates distances between data points, and everything else is done classically. Training, the model, prediction, whatever. So I think this is a very nice hybrid method, which you can do quite easily. Your quantum computer only has to be able to prepare a state that encodes data, which it sometimes can do generically, like in squeezing. Okay, no, squeezing is also difficult, but you can think of situations where this is very easy. And it has to be able to evaluate inner product. So let's say you need a special purpose quantum computer that can do the swap test, and that's your device. Okay, so let's think about this, is what I tried to explain. So the quantum device just produces the kernel function between data points. And so we did that for the squeezing kernel, and I know this is like, Francesco told me like someone once walked out of his talk because the data he showed was too easy. So I'm literally now thinking of 2D data because I'm more interested in visualizing what happens than in like classifying MNIST or whatever. So what I did here, I basically just took this kernel, the squeezing kernel I just showed you. It was this like funny mathematical function. And in Python, you can just throw in any kernel you like into a support vector machine. You just write your own function and you throw it into there. And this is what I did, and I tried to classify this data, and you see the orange points are the test set data, and like these red ones are the training data, and here the darker ones are the test ones. And this is like your error on the training set, this is your error on the test set. And you can see, I mean, it's not a surprise because this kernel is almost Gaussian shaped in a way, so we can actually classify things quite nicely. And this here is this parameter, this hyperparameter. And I thought it would be funny. I just made like data in the shape of the logo of Xanadu. And this is just to show that if you vary C, so there's a C where kind of like sometimes it's more difficult if you have like smaller margins and it's easier. So this hyperparameter C can sometimes like help you to like get more fine data or like draw like small decision boundaries in smaller margins. Oh yeah, and now, oh, okay. And now this was just, so, okay, let me just refer to the paper. There's an analysis why this works, so why the squeezing feature map actually makes data linear independent, and that linear independency makes data linear separable in Fock space. And to test this, I just like also put a perceptron classifier in Fock space. And you can see, this is a bit quick, but you can see that it totally overfits the data and gives me a training error of 0 if I just wait long enough. So this is just to show that the data is actually linearly separable in Fock space. So this feature map seems to, I don't know if you always want that, but it at least seems to like do something that makes the data go like further away from each other and gives us more play. And I think, okay, last thing, I don't want to think about squeeze up, but speed up, but if you make this, this like input encoding circuit intractable, you have a classically intractable kernel. So in theory, you can actually show quantum supremacy in this framework. You just like hope that this kernel is also useful for machine learning people. Okay, and the second approach I will only glimpse over. We can also now go into, because our feature space, our Hilbert space, we can also now use quantum computing to classify directly in Hilbert space. So we this is like basically just these two like squeezed modes. So this is, after this operation, my data is mapped into a feature space, into Fock space, and then I can apply a variational circuit and somehow read out data. And so this is just the answers for the circuit. Maybe that's not so important. What I want to say is what this does, if you think of a neural network world, is it takes two inputs, it projects it into a layer of an infinite dimensional Fock space, and then it kind of, again, takes like two outputs out. And also that can classify data quite nicely, and it's like, well, I don't know if that's good or not, but it's 200 epochs, like in this case, to actually like, classify the data, learn this variational circuit. And lastly, I think okay, if I have a minute, my watch is like wrong. Oh, really? My watch is really wrong. Okay, cool. I have a battery-free watch, and it sometimes just stops, so it's not a very good idea, right? Okay, no, this is perfect. So, so let's say I think I need another 5 minutes. I want to give you a teaser about this work with Microsoft, which was more on variational circuits. And right in the end, I want to show you again how this method that I just discussed gets away or like pushes away all our problems with it. Well, not all our problems, but it could be a very interesting like plug-in to this. And also here I stay like on a very like abstract level. So think of this as a step in a recurrent neural network. I've got, for leaving neural networks, I actually speak about them quite a lot, right? Yeah, anyways. So I've got an input like layer where I feed like an input vector into, and then I've got like some connectivity between it. So I've got like, so basically this is like just a layer of a neural network, and the output units have the same size, or the output layer has the same size, simply because in a recurrent neural net, the units are always the same, but you update them in time. So you can think of it, or think of it as a feed-forward network. I don't actually care. And so there are nonlinear activations here. And in the classical literature, interesting enough, I'm sure some of you saw it and also like immediately like thought, whoa, there's so much potential. Some of actually the big guys, so was Joshua Benjo, actually said like, so we've got in the lots of recurrent neural networks a problem with vanishing gradients. Someone mentioned that in a talk before. And he said, or the team said just like, let's take this matrix, this weight matrix, and make it unitary. Because unitary matrices preserve length of vectors. So they preserve, in a sense, like the amount of gradient that is there. So the gradients won't vanish. And what they actually did, they kind of like decomposed this unitary into like lots of matrices. This is a diagonal matrix, Fourier transform, reflection, permutation. All those matrices are really familiar to us in quantum physics. So like, I think everyone who read this paper must immediately have thought like, whoa. So what we did is thinking about like, what happens if we just like put a quantum circuit here? So now you immediately like see there's one single problem, because this is now a linear evolution. Or actually, I showed that in the previous slides. But as I said, like the classical people actually put an activation function on here that's nonlinear. But let's just say we take a linear layer, and then we just like use a quantum circuit instead of a weight matrix. And so this is kind of, we have like so if you say we take a variational circuit, and I'm sure you find more and more papers on this idea soon, actually, like in the archive, because this is like an idea for hybrid technologies and like, well, intermediate term devices, quantum devices that's coming up. The moment I say I take a variational circuit, it's just 0.1% of your work done. Because it's almost like a machine learning person to say like, okay, let's do machine learning, but which model do I use? Which circuit architecture do I use? Like, how can I theoretically like infer if this model is good for my data? Or like, there are a lot of like open questions. Can we like formulate new like learning algorithms that are maybe not inspired by classical learning algorithms? Maybe backprop is really bad for us. Probably is. So just also as a highlight, like we like thought about like circuit architectures that consist of single qubit gates. They're like fully parameterized, so this could be any single qubit gates, and controlled single qubit gates, just to like keep it simple and make it like easy to implement on a general computer, whatever you want. And we try to like be informed by making a circuit maximum entangled, so like making the circuit like entangle states as much as possible. The idea is we want to like capture correlation in data, so this like guided our like circuit design. And so this is a viewpoint that I find super helpful. I don't know if you find it helpful. Actually, like each of these quantum gates, if you write them down or you try to program them or like implement them in a simulation or something, is obviously a matrix, right? And then I thought if it's a matrix, it's actually something like a linear layer, right? It's like it induces some connectivity. And so just to like invite you to maybe like follow this way of thinking about it. So like if I have 2 qubits and this is a single qubit gate, I hope I got it right because it acts on the first qubit, then the matrix that this implies has this structure, right? These 2 entries are the same, whatever they are. And this actually implies a layer because you see if this is like the connectivity from 1 to 1, this is the connectivity from 1 to 2, it's 0, so there's none. This is from like 1 to 3, and so on and so forth. So actually a qubit gate is a sparse and weight-tied layer in a neural network, and highly symmetric one as well. And if you actually have these conditional quantum gates, you actually destroy a little bit of symmetry. So you have these like, you kind of like just like take the value that's here and put it here. So this is the unit like transformation. So you can think of, okay, I'm coming back to neural networks again, but like you can think of quantum circuits actually as a certain type of linear layer that does a parameter tying. Nicely enough, they're unitary because otherwise you might get problems with having deep architectures because you actually make a super, super deep layer by a very deep circuit. Even like 30 gates is a 30-layer neural network. But I'm very sure that this is actually not a problem in this case. It's an interesting question to actually say. Another highlight, I think the last one, is from that paper that I won't go into, is so if you now do backpropagation, how do people usually do it? So if they have a variational circuit, they have to like calculate derivatives of that circuit. And since this might get messy, or like a big problem is that if I take a derivative of a unitary, it might not be unitary in the end. So what people usually do, they just like use finite differences methods and try to like use numeric gradients and don't calculate these analytic gradients. But in our architecture, and it's pretty general, and I think Fahy and Neven also have a similar approach for a slightly different idea, is that gradients of circuits are non-unitary, but they're weighted sums of slightly different circuits, which means for us, practically, we can just run we have one device, we run it slightly different, maybe 3 times or 4 times, and add the result, and we get analytic gradients. And this might be very useful for training of variational circuits. I don't know, but yeah, at least because it's so these numeric methods, they're very error prone, and our results are already very like noisy. So you add noise to noise. So at least if you've got the analytic gradients that you like take out of your quantum device, you can hope that it's a little bit better. And I don't know, we heard that that there were a bit of trouble with noise and gradient descent with numeric methods. So maybe this helps, I don't know. And now the last one, I want to unite now plug my feature map idea into that. So now obviously, maybe some of you might wonder now if we like just apply like a unitary here, we don't have nonlinearities. And how do we put nonlinearities into this? This is actually a question that I was thinking about for years. If you have if you interpret this as an amplitude vector of a quantum state, you apply a unitary to it. How can you now induce nonlinearities that actually simulate neural networks? And now my answer is actually super simple. By just mapping information, by just using feature maps to map information into this first quantum state, I already do all my nonlinear behavior. I just need a linear classifier. So I can actually use what quantum systems like naturally give me, which is linearity. So, and remember, the feature maps are not something complicated. They're literally just what I already do very often, which is encoding information into a quantum system. But then now there's like lots of questions that you can have. What does that mean to actually choose a feature map and learn a circuit? It's kind of a double learning like model. Is that a much richer model even, or is that interesting in some contexts? What does it mean to learn data or like classify data in a Hilbert space? Like, what does that give us? So I think this opens like a lot of questions. It gives us methods to use, and especially in variational circuits, this feature map idea might get rid of the problem of implementing nonlinearities that we have the moment we use amplitude encoding. We don't have to do things like repeat until success circuits for neurons or like all these fancy ideas. We just work in a super large dimensional feature space and outsource our nonlinearity to the feature map. Okay, I think that was it. Yeah, exactly. Thanks.
Thank you. questions? There's one.
As more of a comment, that squeeze state with all the Fox state and all that, it's not that hard. That's easy to make squeeze states.
It depends on how high the squeezing is.
Oh, it's hard to make good squeeze states. Yeah, that's right.
Yeah.
So the algorithms that you've been talking about in this talk, are they sort of like these in the limit of infinite squeezing type algorithms, or are they more like correcting for finite squeezing effects?
Yeah, so also we had this initial idea to encode the data into the squeezing, and then we ran into a lot of problems because obviously squeezing means how much energy you put in the system, and this is sometimes also influences your probabilities, and then inputs and outputs will correlate in a funny way, but you're right, I think this is fairly similar, but obviously no one would do that because it's classically super tractable, right? But maybe there's something a little bit more complicated that kicks us out of that sphere, and
Okay, we have one more question here.
So you mentioned that the nonlinearity can be just implemented only at the feature map stage, and then the later can be just linear. Mm-hmm. But I think if you want to handle more, complicated features, probably you may need a more, nonlinearity, more stages.
I think this is something that's implied for neural network research. Because the more layers you have, the deeper, the more features you can extract. But support vector machines worked for years just using these feature maps as a source of nonlinearity. So I really invite you to think about it really as, instead of compression, you do something that's very similar but the opposite way around. You do an expansion. And I actually forgot to mention the main theme of the Microsoft paper was to find out if we've got we are classifying these vast Hilbert spaces, but we only have a few parameters, how can that actually work together? So because we actually have a logarithmic number of parameters in terms of the model, and we also our data is basically just comparing classical models that are quite stupid, but use all more parameters than ours to this model, and show that we can actually get away with that. Okay, yeah, so.
Okay, Vedran?
So, thank you for the talk. It was very, very nice, and I very much like your feature map idea. I have a genuine question. This is really, really a question. There's something called the covers theorem in kernel methods, right? You ask this question of why it turns out that if you raise it via this Gaussian kernel, via the squeeze kernel to an infinite dimensional space, why your data becomes linear separable. But isn't this by necessity? Always, don't all your data points become support vectors? And if that's the case, then my question is, doesn't this completely kill the sparsity of the model?
Hang on. I can't connect right now that you say I want them to become linear separable with the support vectors.
I mean, Covers theorem tells you that if you go into a high enough dimension, all your data points are always going to become linearly separable, right? But this also implies that all of them can become support vectors. And then you go from a situation when you might have a simplest case with small errors, like where you allow select variables, to a situation where you have zero error, but you have optimal overfitting, right?
Yeah. No, this is what I'm saying, my hope, or maybe this is a naive hope, but the idea of taking variation circuits now with these vastly lower amounts of parameters are an ansatz for a model. And the hope is, and this is a very open question, that this works like regularization. So that they actually decide, so what he's actually asking, if I map data, let's say I map data to basis vectors, so they're super separated from each other, right? I can always cut through everywhere. But if I learn on some of these basis vectors, I have no idea what happens in the other dimensions. So I basically can totally overfit my model and train it super nicely, but I have no idea what's actually happening with any test case. And and that's very valid. But my hope would be that we can introduce linearization, regularization in the second step. Or make better feature maps, because, Gaussian kernels have the same, should run into the same problem, right? Yeah, and there's also internal regularization mechanisms from a support vector machine. So we have to source that from somewhere,
All right, more questions? Well, if not, then let's go for a poster section. But before that, let's think.